Okay, students. Welcome back to this lecture. Today we are in chapter 5.1, still numerical approximation of DAEs. Today we really gonna go trying to solve a DAE with a Runge-Kutta method. RKM is Runge-Kutta method. But we will need first some notions how these RKM methods look like for ODEs. We had this last week, and we already implemented some. But to set the notation, we need a little repetition again. But then we will look what happens if we apply such a RKM method to these easiest DAEs, linear DAEs with constant coefficients. But let's see. So numerical approximation. Well, this slide will be very quick, but you had a lecture last week, and I hope this is all clear then. But still, we will refer to a number of these concepts again. And let me draw this picture again, just that we know what we talk about. Here we have the T0, here we have the TE. That's what we are interested in. And well, let's assume this is the actual solution. That is x of t. So here's the timeline t. And well, it doesn't matter so much whether this x of t follows the dynamics of a DAE or an ODE. So that's really all the same. And then, well, as I said, instead of, we're certainly not able to compute the actual solution, but what we can do is using a discretization of the time grid, so just at a few points, and try to compute the value of the solution at these points. So this here is x0 that we have. This will be x1, this will be x2, and they will be like, so xi should approximate the solution at time ti. And then, well, what we also assume is that we have equidistant grid. This means that ti plus 1 minus ti is always the distance of h. So this is h. Well, what else do we need? Well, no, the n is not so important right now. Okay, maybe a little regression on what does mean equidistant or not. If it's not equidistant, so often one uses adaptive grids, then one has actually ti plus 1 minus ti is hi. So the difference can change in every time step of but then let me see how this gets out. But then we will have these error estimates like we had it last week. Say the error is more or less a constant times c h to the p that we had, and now if there was an I, then we have this for every hi, but this will be of course always smaller than if we took the maximum h max, and this is the largest step size. This means technically, one can always take the maximum and have these error estimates, but this is a lot of notation. That's why we want to stick with equidistant grids. But well, really in practice, one wants to use adaptive grids. Okay, what else do I have to explain here? Then we had these one-step methods, where we said that the new solution, so xi plus 1 might be the x2 computed on the base of x1, is defined through this phi function, which depends maybe on the time, on the step size, on the previous step, and whether or not we have an implicit scheme, maybe on the value itself. And implicit schemes will be very important for solving DAEs. Maybe already a little outlook okay, multi-step methods. We will get back to that. That one will have that xi plus 1 is phi of ti h xi, maybe xi plus 1, but then also some previous, say xi minus 1 and so on, xi minus k. This can happen, and that's then a multi-step method. We had the local consistency error. Which is defined as EH as, well, basically putting in here the exact values. So x of ti plus 1 minus phi ti h x of ti plus 1. Yes, so here you see, for example, here is the xi, which is the numerical quantity. This is the numerical quantity. Here's the exact quantity. And so local consistency error examines what error is actually caused by the phi function, by the method itself. And then one looks for estimates like EH is O to the HP, and this means well, basically that one can bound this by a constant times h to the p. Okay. All right, then we need to have another quick look on Runge-Kutta methods. And I will really just use the RKM to abbreviate this. Runge-Kutta methods. They are defined as, so they are one-step methods. And they are defined like xk plus 1 is xk plus h some, oh no, shouldn't. So we want to have the I here, xi. I hope I can be consistent and always use the I for the time step. So j is 1 to s. Beta j xi j with a dot. So this one needs this beta, this is the parameter of the method, and then one needs these xij dot, the stage derivatives, and that's, so to say, the task to compute these xij. Okay, shall I write them down here completely? Okay, I can. So these xij dot, they are defined as f of ti plus gamma j xij, and here this is needs to be defined for all of these j. So j ranges from 1 to the s. Now we have here something new, actually a helper. On these xij without the dot, the stage values are called, they are given as these xi, which was this very xi, plus something that actually looks like this, but is similar but different. Here we have the h. We also have the sum. Now the j is already taken, so we take the l to sum up the alpha jl. Actually, this alpha jl are more or less these beta, but they, for every j we need another one. And here we have again these stage derivatives xij. And actually those both together, well, you can take these and insert them here directly. So this basically this is a a nonlinear, maybe implicit equation system for the xij dot. Well, and once we know them, then we can compute the new increment. And let me tell you that this method is basically defined by. Okay, sorry, I have forgotten to say that this is an application to such an ODE, f of tx. And this is basically defined by, where do we have it? Defined by the beta j, beta 1 to beta s. That's defined by s, which is the stage, by the gammas, gamma 1, gamma s. These are these values here. And then the alpha 1, 1, alpha SS, alpha 1s, alpha s1. So all this matrix. And this one writes into this butcher tableau. Here this is this A matrix. Here one writes down the beta. Here one writes down the beta transpose, and here the gamma. Well, okay, the one. All right, you know what I mean. Okay, so this is a Runge-Kutta method and a general term, and then we will need question stability, and you can show that one step methods are stable, and this can, for example, seen in Kuhnke-Meerman book. There's a definition for what is a good notion of stability in this case, and then it always also shown that one-step methods are actually stable. It's the beginning of chapter 5.1. And other question is consistency. And since the method is defined by the S and then all these parameters, one can already assume that also the consistency of such a Runge-Kutta method depends only on how we choose these parameters. And in fact, there is this theorem by Butcher. That says the RKM alpha gamma beta transpose is convergent of order P. If there exists PQR such that these coefficients gamma, beta, alpha fulfill the conditions. Okay, I don't want to write down these number of conditions right now. but one needs to have that PQ already wrong. This one condition B of P is fulfilled, the one is the C of the Q, and the other one is the D of the R condition. And these additional conditions, that one needs P less or equal than Q plus R plus 1, and also P must be smaller than 2Q plus 2. Okay, but well, the thing is that these number of these bunch of coefficients of the method have to fulfill a number of conditions that you find in the script or in the book by Gunkel and Mehrmann and many other places. Just tell you this is theorem 5.1 in the script. Yeah. And if this is the case, then one knows that this RKM method is convergent of order P. Okay, and this is insofar interesting for us because it helps us to understand the Runge-Kutta method, and then we will derive similar conditions for application to a DAE. Okay, good that I have some space left because we are still in the ODE case. So the RKM applied to this x dot is f of t and x is convergent of order P if we have these numbers P, Q, and R such that the coefficients fulfill these conditions. Okay. All right. Okay, and then we need some more technical definitions that will be helpful for the analysis as some linear algebra definitions. First thing is the kronecker product. It takes two matrices U and V and maps them to the kronecker product, while the okay, that's not so well written. Well, it takes this pair of matrices U and V and maps them onto this kronecker product. Kronecker product can be made for all sizes of matrices. If you recall the definition of the actual matrix product, the sizes of the matrices have to be compatible. It's not the case for the kronecker product because this will be a huge matrix. So whenever you see this kronecker product and you have huge matrices, then don't do the kronecker product because this will blow up the dimension a lot. Because here is like the first entry of the U matrix times the whole of the V matrix. Here there will be what dimension did I take here? The M. The last entry, but again the whole matrix of the V. Here we have U1N. Again the full V matrix. Well, and again the full V matrix. Maybe to get an idea. So if this was a 4x4 matrix times a 2x2 times a 3x3 matrix, this will be this little entry here. Okay, maybe give it a color. times the full matrix here. Well, same here. Okay, so that's a Kronecker product. It really blows up the matrix dimensions by taking the product of these matrix dimensions. Okay, maybe that's a good illustration. So I'll say here's this green entry, and then here's the green entry. And since it's just a scalar, one can just take the scalar multiplication of a scalar and a matrix. Okay, so this is the Kronecker product, and it has the following properties. So if well defined, then one knows that v times r times s is r times vs. So, and this is the standard matrix multiplication. And well defined means that one has to, since this is standard matrix multiplication, then this product has to be well defined. And then there is this other, so there exist permutations, and they are called the perfect shuffle. Perfect shuffle, sorry for this typo, P1 and Pi2. So that Pi1 transposed U times V times the Pi2 is V times U. So like most products, the Kronecker product is not commutative, so one cannot change the order here, but well, one can resort them always such that one can take this product, but then resort it a bit, and then it's this product. So it's the product of V times U. Here we have the product U times V. More if UV are equal size, then P1 is P2, and then we will just use the pi, and well, we will make use of actually of this pi. So if these matrices U and V have the same size, and they I hope they will. Maybe not. But yeah, if they have the same size, then they can be resorted by just one projector, by just one permutation matrix. Maybe another little regression permutation. It's basically resorting columns or rows. And of course, such a resorting can always be undone. Can be undone, and in particular by the transpose. So the pi t does the transpose, and all this means that pi times pi transpose is the identity. And this in particular means that the pi is invertible. And yes. Okay, so far so good. No. It's not that we need. And also it's wrong in script, but I So if u and v are square matrices, that's it. If they are square matrices, then then this works. I have to fix it in the script. Then I also wrote equally sized. Okay, so if they are square matrices, and that we will use a lot, then there's just one permutation we can use from the left and from the right to like make this product here commutative. All right, but now, yeah, I think now we are done with. Now we can start. So Runge-Kutta methods for DAEs. Finally, maybe one or the other of you took the course to learn about how to numerically integrate DAEs, and now we are at it. Okay, and the main problem, so if we look at the definition, actually we don't really have here this was the stage derivatives, and in the DAE we don't have this explicit representation of the stage derivative, so we don't have I'll write this down here. This actually looks like x dot as f of t and x, and that's not an ODE, but in fact it's very easy. So this is ODE, and now we go to DAE, and there we will we actually have this like ex dot as f of tx, so this can be a DAE. And this then means that for the stage derivatives we do the same. Xij dot, so we just add the E matrix here as f of tx. And maybe even further regression when we go to the DAEs and its most general form, that the DAE has just this closed form f of tx, but then we just put in here the stage derivatives and the stage values. So then we have this equation here, then this will become f, so equation for xij dot will be f of ti plus gamma jh, that's the t here. Then we put here in the stage derivative value, and because it's implicit, we have to put this here as well. Okay, so much for how one can formally apply a Runge-Kutta method for DAEs. And that's how we start. So we start with ex dot as ax plus f of t. Linear constant coefficients. We are new to this topic, so why not use easy scheme like explicit Euler. Okay, let's see. One step of explicit Euler would actually look like ex I plus 1 as exi plus h a xi plus f of ti. Okay, but since these not invertible, since the E is not invertible, no way to compute xi plus 1. Well, we cannot invert this e, meaning there are parts in the xi that are not defined. So there's no chance that we can compute the new iterate based on the old one. So obviously this is not a good idea. Well, but implicit Euler works well. Namely, here we will have again is exi plus 1 is exi plus h times a, but now we have the new value here, xi plus 1 plus f of ti plus 1, which will then become e minus h a xi plus 1 is exi plus f I plus 1. Yeah, actually that's like a short notation for f of ti plus 1 times the h. Don't forget this. And well, do you all recall what is regularity? So if EA is regular, and actually that's something we should assume because we want to approximate the solution, and if it's even not clear whether the solution exists, or even worse, if there are maybe many solutions, then you don't know which one you will actually approximate. So it's very reasonable to assume that this pair EA is a regular pair. But this in particular means that E mean minus HA is invertible for almost every H. So there might be a few H for which this is not invertible, but they are only a finite number. So yeah, and this means we can compute xi plus 1 from here. And well, this now was just a little warm up to tell you that, well, first of all, how to apply a Runge-Kutta method for a or in this case a very easy scheme for a DAE. Well, just basically at the E matrix. Other thing to take off, that explicit Euler scheme does not work, and I will show you in a second that this is true for any explicit scheme. Explicit schemes won't work, but this implicit Euler scheme works well, because, well, regularity implies that this matrix here is invertible typically. So if it's not, take another H. If it's not, then take another H, and after a finite number of tries, you will have an H for which it's invertible. Okay. Yeah. So generally, that I want to do right now. Generally, now in all general, we apply a general RKM, which is basically these alpha, beta, gamma to the DAE EX dot is AX plus F of t. And since this is linear, we will have that. I have to go back to this here. So we will have to solve this equation system here, which might be nonlinear, but if the equation is linear, then it's not nonlinear, then it's a linear equation, but it's implicit. And what is important are these xij values. So we have to solve for these values. And there will be an exercise. That shows you what I will now just state here. So if we apply a general RKM with A, B, gamma, A, alpha, beta, gamma to the DAE, then this is the same as solving this I as kronecker DAE minus H A kronecker this curly A, this, oh no, wrong. So H this curly A kronecker the A matrix, this A matrix, times the huge vector x, which we denote by xi, is the same as zi, and the zi is defined as axi plus fti plus gamma 1h up to axi plus fti plus gamma sh. So this is this vector, and for this xi dot vector, which is, you may have guessed it, xi1 dot, here are all the stage values that we need. xis dot, xis dot, and this is exercise to show if one applies a Runge-Kutta method. So this Runge-Kutta method with these parameters here, the beta are not okay to this DAE, then this is, well, what you see here is basically this. Here are the gammas. Here is this S. So a general S stage RKM method. Here's this S matrix. Okay. You have to solve one large linear system for the stage values, and once you have the stage values, you compute the next iterate as, so once you have them, then as it's xi is xi plus h. Here you have the betas again times the stage derivative values. So as I said before, this is important to compute those. Okay, and the question is this well defined? Well, if this here is invertible. Well defined if this matrix here I as E minus H A kronecker A invertible. So we will now analyze what happens here. And okay, so I hope I could convince you that reasonable assume that EA is regular. This means particularly there is P and Q, so that P, E, Q, P, A, Q is in Jordan canonical and Kronecker canonical form, which is here the I, here's the N, and the J and identity. Okay, so this was regularity. We already thought that this is very reasonable to assume, because existence and uniqueness of solution is, so to say, mandatory to do numerical approximation. but if it's regular, then we have also these P and Q matrices so that we can transform the system like that. And well, and now what we will do is consider mistake. Consider I as times this P matrix times this matrix here, times the coefficient matrix I as E minus H A times the A I as times the Q, and this is by lemma. So this is by this property of the Kronecker product. This one. So a product of Kronecker products can be the Kronecker product of the products. So we have applied this a number of times, and in this case this is lemma 5.2 in the script. Well, this basically becomes the P acts, can be shown to act only on this A matrix here, on this part, and same with the Q. So we have to apply this twice. This is one lemma of the product rule here. But we get that this is I as times PEQ minus HA times PQ. Okay, and this is already interesting because, well, now we have like the Runge-Kutta method defined in these matrices in Kronecker form. But what we already can state is that RKM are invariant under equivalence transformations. Which in particular means that we will not change anything if we do so the stage value, they will be more or less, they will exist, and they are defined one by one in a one-to-one correspondence for any system that is equivalent under these equivalence transformations. So what does it mean? Such a state space transformation and the scaling does not affect whether the Runge-Kutta method works or not. So this is important, but we can also use this now to think about solvability, whether this parts here exist or not. This already looks quite tempting to analyze this, but yeah, doesn't help too much at this moment. But what we're going to do is use this other lemma 5.1, the perfect shuffle. Since we know we have square matrices, we can have that this is P, where did we have the pi transposed I as PEQ minus HA PAQ times pi as, well, interchanging these products. That is as PEQ times the IS minus PAQ times the IS matrix. Okay, and this is now much nicer because, let me write this down for you. This is the same as PEQ was looking like identity n times the is minus, no, this is of course not this, this is h times the a. So this is PEQ times the IS, and here we have PAQ, which is this Jordan identity times HA. Okay, and this looks like, so if you recall what is Kronecker product, it's the entries times the other metrics all the time. So this can be straightforward. This can be written as in this form. And here we have n times the IS minus j times HA. And this here is I times HA. Okay, so by all this, so this does not change solvability. So this is multiplication by invertible matrices from the left and the right. We can think of the P of the E and the A being in this Kronecker normal form. So we can actually consider this matrix to be the coefficients. Then we can resort them, and again resorting does not change solvability in no way. So we resort them to interchange these coefficients, and then, well, actually we can assume that we have this system here to solve. And now what does it mean? If we look at that system, first of all, it somehow completely decouples. So we will have to solve this system here, and this is an ODE system. So this is what the same Runge-Kutta method would look like if we applied this to this ODE. x1 dot is jx1 plus f1. Okay, and here we have the special DAE system. DAE and x2 dot is x2 plus f2. So this is nicely decoupled, and well, we can do analysis of the Runge-Kutta method in this form here. And so first thing that we see is ODE part, and then, well, here we have I Kronecker IS minus J Kronecker HA, and this matrix is invertible if H small. You see this basically is a huge identity matrix. So here we hear a lot of identity, that's a huge identity matrix, and here's this vector H. So if H was 0, then identity of course is invertible, but if H is very small, then one is very close to the identity. So this is invertible if H is small, and the other part, the DAE part, I'm already done with my slides. All right. So the DAE part is n Kronecker IS minus I Kronecker HA. If n is like this, in this form, and we would just assume that this is one Jordan block here. So if n is in this form, then this part reads 0, a huge 0, IS, 0, IS, 0. So we have this matrix, and here we have identity times the HA. So this is here we have, just put it here. So this is the this matrix, identity kronecker. The matrix is just this matrix on the main diagonal, and this is then minus HA IS minus HA IS and so on, minus HA. And this is invertible if and only if A is invertible, which is if and only if RKM is implicit. And that's a very important message. Only implicit methods applied to DAE are, well, you can expect reasonable approximations, because otherwise the matrices that underlie this, the numerical procedure, they are just not invertible, so there's no chance to come up with a useful approximation. Okay, but anyways, I just want to sum up everything. Summary. Applying RKM to DAEs. First thing is invariant for these PQ transformations. Transform can assume that EA is in kronecker form. Kronecker normal form. Secondly, RKM decouples. Can consider this x2 dot and x2 as x2 plus f2 part separately, and well, diagonal block structure of this n, which is basically n1 some other parameter. So we have this block structure of this n matrix, and this means can assume that this n matrix is basically given as just one Jordan block 1 1 1 in R to the new, and we will consider these systems which is given as n x dot as x plus f, and n is just one Jordan block and of the size, meaning it's of index new. Alright, so much for today. Next week we will do some very hard analysis of the Runge-Kutta methods. But yeah, talk to you. Bye bye.